In this video, I'm taking a look at integration using the inverse trig functions. And there are three forms that we have. I'm going to do two examples with each of these forms. The first, notice we have square root in the first. We do not have square root in the second. And we do have square root in the third. Also, this third has this extra factor of u in the denominator. Notice that in this case, we have square root, but it's the constant squared minus the variable squared. Here, there is no radical, and since this is addition, it doesn't matter what order these two are listed. It does matter what order these are listed, because a squared minus u squared is not the same thing as u squared minus a squared. However, the addition can be in either order. Here what we have is the variable squared minus the constant squared. This is the constant squared minus the variable squared. That's the indicator that this is the sine inverse form. And the integral form is, this is sine inverse, this is u over a. Where whatever variable is getting, whatever constant is getting squared, that's the value of a. Here, this is tangent inverse. And the way I like to think of this is, as you go down the scale, you increase the complexity. Yes, this still has u over a, but tangent inverse has something sine inverse doesn't. Tangent inverse has a factor of 1 over a. And then finally, secant inverse has the 1 over a, which tangent inverse has, but sine inverse does not. Tangent inverse has u over a, which sine inverse has. So as you go down the scale, you're increasing complexity. Secant inverse also has absolute u over a. And so these are the integral forms. What I'm going to do is go through two examples of each of them. All right? So first, I'll go through two examples using the sine inverse form. And the first example I have here is, I have 16 9 minus 4x squared dx. Now, each of these is really, it's just a variation on a u substitution. The difference here is we must also, this is the sine inverse of u form, because this is the constant squared minus the variable squared, and it does have the square root. So we know we're using sine inverse form. What we need to do is translate this into the generic sine inverse form, write the sine inverse solution, and then translate back to the x. We need to account for everything, including the value of a. A, remember, this 9 corresponds to a squared. And so the question is, what constant is actually getting squared? If you like, you don't need to rewrite this, but you can think of this as 3 squared minus 2x quantity squared. Again, you can think of it this way. You don't necessarily need to write it, although you're certainly free to write it that way. But we need to think about what constant is getting squared to create 9. Well, it is 3. What variable expression is getting squared to create 4x squared? Not just 4x, not just x, but 2x quantity squared produces 4x. And so the role of a is getting played by 3. The role of u is getting played by 2x. Not 2x squared, it's 2x, because we can think of 4x squared as 2x quantity squared. So even if we don't write this, and typically we don't, after you get used to doing this a few times, you don't need to write out that piece. We still understand that this is 2x is the quantity getting squared. We still need to find the differential line. So this implies that du is equal to 2 dx, just like an ordinary u substitution. I don't want 2 dx, I want 16 dx. So the multiplier needs to be 8. And so the substitution is exact. So what we have is 9 is a squared. 4x squared is, don't write it as 2x, write it as u squared. And then 16 dx, we can write that as 8, 1 in the numerator, du. And except for this constant multiplier, that is precisely the sine inverse form. And so now what we write down is the answer for the sine inverse form, which is sine inverse of u over a, and then translate back in using both of these statements. This is the sine inverse form where a is 3 and u is 2x. So this becomes 8 sine inverse of 2x over 3 plus the constant, and we're out. So account for everything, including the a, including the u, account for everything, write it in the generic form, write the answer in the generic form, this constant multiplier just multiplies along, and then go back to the original variable. So let's see if we can do another like this. We have the integral of cosine of x over, I have 4 minus sine squared of x square root dx. This is, notice it has the form, the square root of constant squared minus variable expression squared. Remember, this is sine of x, quantity squared. This is the sine inverse form because it's constant squared, this is a squared, minus, this is u squared, where a is 2, that's what's getting squared, and u is sine of x, that's what's getting squared here. Form the differential line, so du, the derivative of sine of x, is cosine of x dx, and that's precisely what we wanted it to be. The substitution is exact. So rewrite this. 4 is a squared. Sine squared is u squared. The numerator is simply 1 because cosine x dx is entirely du. And there is no constant, well, the constant multiplier is 1. There is no extra constant multiplier here. So write out the solution. This is sine inverse u over a. And then translate back to the original variable. U is sine of x over a. A is 2. And we're out. So that's the technique for dealing with the sine inverse form. And the next couple of videos, I'm going to go through 2 examples using the tangent inverse form and 2 examples using the secant inverse form.